Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Distillation, how to calculate reboiler heat duty. In this video, you will learn the steps involved in the process design of the distillation column, how to calculate the reboiler vapor quantity, how to calculate the reboiler duty and steam required for the heat duty. Please subscribe to the channel. By subscribing, you will motivate us to produce knowledgeable video content for you. So subscribe now before you forget. Distillation is an energy-driven process. Energy is needed to produce vapor that is required to bring about vapor-liquid contact on the stages for mass transfer. It is this vapor that is finally condensed in the overhead condenser to produce the reflux and the distillate product. Reboiler is an important equipment in the distillation column. It consumes energy and serves to provide the vapor to the column. Energy is added in the reboiler and removed in the condenser. In the design of distillation column, calculation of heat duty of the reboiler is an important step. It forms a part of the mass and energy balance of the column in the design. The heat duty corresponds to the energy consumed for vapor produced in the reboiler. Shown in the figure below is the distillation column with a total condenser and a partial reboiler. The heat duty to the reboiler is provided by steam. Cooling water is used as utility in the condenser. We will consider this distillation system for calculation of the reboiler heat duty in the subsequent discussion. The steps involved in the process design of distillation column, including reboiler heat duty, is provided in the diagram below. Fix the column specification for feed split. Feed F, distillate D, bottom product B, feed composition XF, distillate composition XD, and bottom composition XB, and the feed quality. Find out the minimum reflux ratio or minimum. Take actual reflux ratio as 1.2 times or minimum. Determine the number of theoretical stages NDS and the location of the feed stage. Calculate the reboiler vapor flow and boil-up ratio. Select the utility steam to reboiler. Calculate the heat duty of the reboiler. Calculate the condenser duty. The first step in the design of distillation column is to specify the design objective. The usual design objective of column is to separate a given feed into distillate and bottom streams of specified compositions. Minimum reflux calculation. For binary mixture separation, the minimum reflux is determined by using graphical method, using a capital diagram. For multi-component distillation, FUG method is used because graphical method is not possible. Operating reflux. The operating reflux L equal to 1.2 times or minimum. Now you have the following stream data: F, D, L, and B. The next step in the design is to calculate the reboiler vapor flow. Reboiler vapor flow is obtained by mass balance as follows. The following mass balance calculations are done. 1. Mass balance around the reboiler. 2. Mass balance around the condenser. 3. Mass balance around the column. In addition, you need to know the following stream data. 1. the quantity of vapor entering the rectification section. 2. The liquid entering the stripping section. The usual assumption of constant molar flow is valid here. The mass balance around the reboiler is shown in the figure below. L dash equal to B plus V dash. The mass balance around the condenser is shown in the figure below. V equal to D plus L. The mass balance around the column is shown in the figure below. Vf plus Lf equal to D plus B. Vf and Lf are the vapor and liquid quantities of the feed entering the feed stage. These two terms depend on the feed quality. The figure below presents the stream data of vapor entering the rectification section and the liquid entering the stripping section. Vapor entering the rectification section equal to V dash plus Vf. Liquid entering the stripping section is L dash equal to L plus Lf. Rearranging the equation for liquid entering the stripping section, we get Lf equal to L dash minus L. Substitute Lf into the column balance. We get Vf plus L dash minus L equal to D plus B. Rearranging, we get B equal to Vf plus L dash minus L minus D. Substituting B in the mass balance around reboiler, we get L dash equal to Vf plus L dash minus L minus D plus V dash. Rearranging, we get V dash equal to D plus L minus Vf. The above equation 1 conveys a meaning that the vapor entering the rectification section is a vapor entering the condenser minus a feed vapor flow rate. Also, we understand that the boil up is related to the reflux. Dividing the equation 1 by B, we get Vb equal to V dash by B, which is equal to L plus D minus Vf divided by B. Vb is called the boil up ratio. The boil up ratio is the rate of vapor produced in the reboiler per mole of bottom product B. Higher the reflux ratio, higher the boil up ratio. In other words, lower the relative volatility, higher will be the boil up ratio. For a given feed, if the product split and the reflux ratio is known, the boil up ratio and the reboiler duty can be calculated. The reboiler heat duty QR equal to delta HV times V dash, where delta HV is the heat of vaporization of bottom product B. If the steam is saturated and loses only its latent heat, the quantity of steam required is Ms equal to delta HV times V dash divided by lambda, where lambda is the latent heat of steam. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.